Welcome to The Explainer. Today, we're diving into something that could, and I mean could, turn physics on its head. We're going to take a look at the radical work of director Yang Bong and really ask the big question. What kind of value, what kind of contribution could this bring to science as we know it? Now, the material we're drawing from today frames this work among some pretty heavy hitters. We're talking about those once-in-a-century breakthroughs that just completely rewrite the rules. You know, the kind of earth-shattering ideas that led to quantum mechanics or general relativity, the stuff that earned Nobel Prizes and literally defined the last century of science. So, the claims we're about to get into, they're on that same epic scale. This isn't just about tweaking a few equations. It's proposing a total teardown and rebuild. Which forces us to ask the question, right? Are we, right now, looking at the very beginning of the next great leap in physics? All right, let's get into the heart of it. And to do that, you have to appreciate the sheer audacity of what this theory proposes. It's not just nudging the current models, it's aiming to replace the very foundation that modern physics is built on. This idea of two worlds is really the key. For 100 years, physics has had this split personality. On one hand, you've got quantum mechanics. It's fantastic at describing the weird, wild world of tiny particles. On the other, you have general relativity, which nails the behavior of giant things like planets and galaxies. The huge problem? The two theories just don't talk to each other. They don't work together. And uniting them, that's been the holy grail of modern physics. And this is where Yang Dongbang's theory makes its biggest, boldest claim. It says there's a direct mathematical bridge between these two worlds. It claims to connect their most fundamental numbers, alpha, the constant that rules the tiny quantum world, and lambda, the constant that governs the massive, expanding universe. I mean, if you could actually prove a link between those two, that would be an absolute game changer. Oh, and it doesn't stop there. Not even close. The theory also says, hey, what if a point isn't infinitely small? That gets rid of messy things like singularities. It also proposes one single elegant framework for all 18 fundamental particles. And while we're at it, let's unify mass and gravity and maybe rethink the famous uncertainty principle with a deterministic twist. Seriously, any one of these would be a revolution. This theory claims to do them all. Okay, so let's take a breath. Those are some absolutely extraordinary claims, so why should anyone give them the time of day? Well, according to the source material we're looking at, the justification for all this rests on two very different pillars: mind-boggling mathematical precision and a surprisingly deep philosophical motive. The first pillar is the math, and the claim here is just staggering. The theory can supposedly calculate fundamental values, like the mass of an electron, to an accuracy of 31 decimal places. Now, if that's true, that's not a fluke. That's not a lucky guess. That points to a mathematical engine underneath it all that is far, far more powerful than anything we have right now. But it's not all about the numbers. That's just half the story. This work isn't being presented as just a cold intellectual puzzle. As the source material suggests, the other pillar is deeply human. There's a philosophical why behind it all, which is pretty rare and honestly fascinating for a theory in physics. And here it is, according to director Yang, the whole quest began with thinking about human suffering and wanting to contribute to this huge question of how should people live. This idea of a good motive is presented as being just as important as the math. It suggests that a true theory of everything shouldn't just explain the universe, but it should also have something to say about our place in it. So let's play this out. If this theory actually holds water, what could it do for us? What's the payoff? Let's explore the potential real-world applications, because this is where we see its potential contribution to science and to all of us. For starters, one of the first places we might see an impact is in computing. Imagine having a theory that predicts quantum behavior perfectly. You could design hyper-efficient, next-level semiconductors, and that's the kind of hardware that would fuel a true revolution in artificial intelligence. And going beyond computers, a totally new physics could literally redefine energy. If you find out the fundamental rules of matter and energy are different from what we thought, that could unlock completely new ways to generate clean, powerful energy, methods we can't even dream of right now. And on an even bigger scale, if your theory is powerful enough to model the entire cosmos, maybe you could apply that same complex logic to better understand and predict massive, complicated systems right here on Earth, like natural disasters. All right, now for the big reality check. Because no matter how beautiful or promising a theory is, in science, it's just a cool idea until you can prove it. So let's talk about the hard part, the path to validation. At the end of the day, this all comes down to the tough, rigorous work of science. First, you have to lay it all out there. Publish the detailed math so anyone, anywhere can check your work. Second, you have to go head-to-head with the reigning champ, the standard model, and prove clearly how your theory does a better job. And third, you have to step into the ring. You have to engage with the global physics community, face the tough questions, and get it peer-reviewed. Science demands proof, period. So we're left with this absolutely compelling narrative. A researcher, apparently driven by a profound desire to help people, who claims to have solved the biggest puzzle in all of physics. The ideas are radical, no doubt. The potential is enormous. But in the world of science, the burden of proof is absolute. The question now isn't just about whether the theory is right, it's about whether the evidence will be presented, tested, and ultimately accepted. Is this a new chapter for physics, or is it a story that's still waiting for its ending?